Imagine a mistake that just saved the pharmaceutical industry from collapsing under its own weight. Today, we are diving deep into the Cambridge lab incident of 2026, where a simple experimental error sparked a revolution in how we design life-saving drugs. What started as a blunder turned into a breakthrough that makes traditional manufacturing obsolete, replacing toxic chemicals with pure light. By the end of this video, you will understand exactly how a tiny slip-up is changing medicine forever and why every scientist should be watching what happens next. Stick around to see the process, the implications, and why this isn't just science fiction, but our new reality. It all began on a Tuesday in March of this year at the University of Cambridge. The team was working on a standard protocol for modifying drug molecules during their final stages of development. They were using what is known as Friedel-Crafts alkylation, a process that has been the gold standard for decades, but is notorious for being messy, slow, and incredibly dangerous due to its reliance on harsh, toxic chemicals. The plan was straightforward. Mix reagents under specific conditions to attach a necessary group to a complex molecule. However, something went wrong. A small calibration error in the temperature sensor caused the reaction vessel to heat up slightly faster than anticipated during an initial test run. Instead of the expected violent explosion or failed yield that should have occurred with such aggressive heating, the mixture simply sat there, stable but transformed. The lead researcher, seeing a weird pattern on the spectrometer that shouldn't exist under normal conditions, assumed it was equipment failure and ran another batch immediately to confirm the result. What they discovered in the second run was not just a repeat of the error, but a completely different chemical pathway entirely. The heat didn't break bonds as intended. Instead, it triggered a subtle electron shift that created a new type of catalytic environment within the molecule itself. This accidental discovery bypassed the need for toxic catalysts entirely and opened up a door to creating complex drug structures in a single step rather than days of laborious trial and error. The real magic happened when they tried to replicate that specific electron shift without the heat, using light instead. In their follow-up experiments published early March, researchers found that by tuning the wavelength of ultraviolet light precisely, they could induce an anti-Friedel-Crafts alkylation reaction. This technique relies on electron donor-acceptor photoinitiation. Essentially, when photons hit the specific molecular structure created during that initial mistake, they act as a trigger that rearranges atoms with surgical precision. Think of it like using a laser pointer to cut glass versus trying to carve it with a dull chisel. The light provides the energy needed to break and form bonds instantly, without generating the toxic byproducts that usually litter the chemical waste streams of modern labs. This shift represents a paradigm change in organic chemistry. Previously, getting from a basic drug scaffold to a complex, multifunctional therapeutic agent took weeks of synthesis, purification, and testing, often requiring multiple steps involving acid, base, or heavy metal catalysts. With this light-powered method, the entire process can be compressed into hours or even minutes. The purity of the final product is significantly higher because there are fewer side reactions occurring during the transformation. Scientists at Cambridge have already begun modeling how this could be applied to existing drug candidates currently stuck in clinical trials. Imagine taking a molecule that requires 3 steps to synthesize and reducing it to 1, cutting development time by 40%, while simultaneously eliminating hazardous waste. This is not just an incremental improvement. It is a fundamental rewriting of the rules of pharmaceutical manufacturing. The implications of this discovery extend far beyond the laboratory benches at Cambridge. They are deeply connected to what humanity has been doing in space since May. During the Artemis II mission, astronauts spent 10 days aboard a lunar spacecraft testing critical life support systems and emergency protocols. In one specific instance, a minor error in the simulation software led to an anomaly that engineers initially dismissed as a glitch. However, similar to the chemical reaction at Cambridge, this anomaly revealed a more efficient way to manage power distribution under extreme conditions. The parallel is striking. Both the drug synthesis and the space mission showed us that what looks like a failure or a mistake is often actually a hidden optimization waiting to be unlocked. In the case of the drugs, the mistake was an unintended electron shift caused by thermal variance. In the Artemis context, the error was likely a misinterpretation of sensor data regarding energy flow. Both scenarios highlight a broader truth about complex systems. They are more resilient and adaptable than we give them credit for if only we know how to look at them correctly. This new light-powered synthesis technique could also be applied to remote or space-based manufacturing. Imagine producing medications on the International Space Station or even future lunar bases using sunlight as a catalyst, removing the need to ship fragile, toxic chemicals from Earth. The stability required for these reactions means they can survive transport through vacuum environments once activated. This suggests that the pharmaceutical industry is looking at a future where drug production becomes decentralized and sustainable, much like the energy solutions we are seeing in deep space exploration. It turns out that the very things that challenged our systems, unexpected errors, harsh conditions, were actually pointing us toward better ways to operate within them. So what does this mean for you in your daily life? The impact is immediate but subtle at first. As pharmaceutical companies adopt these light-powered techniques, the cost of medications will likely drop significantly because less raw material is wasted and manufacturing time is slashed. This could bring down prices on complex treatments for rare diseases that are currently prohibitively expensive due to their intricate synthesis requirements. For patients with chronic conditions relying on targeted therapies, this means access to better drugs sooner rather than later. Furthermore, the reduction in toxic chemical usage makes the entire pharmaceutical supply chain safer for workers and the environment. We are moving away from a model where medicine is produced at great environmental cost to one that mimics natural processes more closely. Automation plays a huge role here. The precision required for light-driven synthesis means robots can handle these reactions with zero margin for error, creating factories that run continuously without human intervention or hazardous materials handling. This also changes how we view automation in general. It is no longer seen as a threat to jobs, but as a force multiplier that allows humans to focus on high-level design and patient care rather than grinding out chemical reactions. We are entering an era where the bottleneck shifts from synthesis speed to design creativity. The ability to tweak complex drug molecules at the final stages of development means we can personalize treatments even further, potentially creating drugs that adapt to individual genetic profiles without needing a custom synthesis plant for every single patient. This is the future of precision medicine, and it is being built on the foundation of what started as just another lab error. From a simple calibration error in March 2026 to a revolution in chemical manufacturing, the story of Cambridge's light-powered drug synthesis shows us that science is often more about discovery than intention. It reminds us that our greatest breakthroughs may come from looking closely at what went wrong rather than ignoring it. As we move forward, this technology promises cheaper medicines, a cleaner environment, and faster access to treatments for those who need them most. If you found this deep dive into the intersection of error and innovation as fascinating as I did, make sure to hit that subscribe button so you never miss an update on these ground-shifting developments. Drop a comment below telling me which other scientific mistakes you think might have led to our current reality. Let's keep exploring what happens when we look at the unexpected.